How are you guys doing here? This is Mike Johnston, and in this video we are going to discuss how to determine whether or not our function has any relative extrema, any maxes or mins, and then how to determine where our function's either increasing, decreasing, or constant. So the way that we're going to go about tackling this is that we're going to tackle this using something called first derivative analysis. So the first derivative test is what we are going to often call this type of analysis. So you probably learned this, well, in my class I know you would have learned this as something called the first derivative test. Other places may call this first derivative analyses. So let's go ahead and do some examples, maybe some more trivial examples, in order to determine exactly what this means. So let's go ahead and just draw a generic function. I'm going to draw a generic function, and it's going to look something like this. So it's going to look something like this, and it's going to go and continue up. We recognize here that this function starts at negative infinity, continues on at positive infinity, and we realize there are no bounds. This is not a problem that is restricted. Therefore, I know that there will be no absolute extrema because this function is always going on to positive infinity. There's always one larger value. This function is also going on to negative infinity. There's also one more negative value. So there's no absolute extrema. However, we do notice here that approximately at this point and then approximately at this point we do have some relative extrema. This is a maximum value. There is a interval. It doesn't matter where the interval is. It could be between here and here. It could be between here and here. But between these intervals, we are going to have a place that has the largest possible value, the largest possible functional value, and that's going to be here. And that's why we call this guy a relative max, because between some random interval that's chosen, it's a random selected interval, we know there's one value that's larger than all the rest. The same thing applies to this portion. Between some randomly selected interval, we realize there's going to be one smaller value, one value that's smaller than every other value, and that's going to be here. And if I were to draw a tangent line through both of these values, let's see if I can do this, draw a tangent line that is through each one of these values, both here and here, we recognize that these tangent lines, the slopes of these tangent lines, have a slope that are equal to 0 because they are completely horizontal. So they have slopes that are equal to 0. So one thing that's very specific about relative max and relative mins, and this is a relative min, is that they have slopes of tangent lines that intersect these points that are 0. They're completely horizontal. So that's the basis of the first derivative test, is that when we find our derivative, we're going to set this equal to 0 because we can also we can use this to determine where we have a max or a min. However, this is something that's specific. Notice over here, notice between approximately here and between here, so maybe this portion right here, notice that this function, as it's increasing from left to right, that our slope here is positive. Our slope here is positive. And then from here to this point, our slope here is a negative value. So we will notice here, if I'm just going to bring down this critical point right here onto a sign. And notice here that if I look at f of x, I realize that f of x is increasing up until this max, and then after the max, the function is decreasing. If we look at our derivative, which is going to be the slope of the tangent line, this is the derivative, we realize the derivative corresponds to the slope, and the slope here for the function that's increasing will be positive, and then the slope here will be negative. So from here, we're going to have the function will be increasing and then decreasing, and the derivative will be positive because the slope here is positive, and then it is negative. And then I'm going to show this over here. I'm going to actually bring this down even further. So if we were to examine this portion over here, so we recognize that still my slope going from this max to this min is still negative, but then after we hit this minimal value and I start traversing my function, I realize that my function has a slope that is positive. So my slope goes from being negative here to a positive value. And that is also going to play into our first derivative analysis. So if I was to drop down, I'm going to drop it down even further. so we can all see it. We notice here that my function f of x and my function f of x, and this is specific here, I don't want us to get confused with my drawing, this will be that 0. So my function here has a value that is decreasing. It's decreasing until this min, and then it's increasing there afterwards. Therefore, we know the slope of the tangent line, if it's decreasing, will be negative and then positive. So this minimum has a functional value that's decreasing and then increasing, and then the derivative will be respectively negative then positive. So that's how we use the first derivative test in order to examine where we have relative extrema. Do make notice that there are circumstances that do not have changes in the derivative, which means that the function could do something like this. It could increase, plateau off, and then continue on increasing. So notice here the function's increasing, increasing, and increasing. Somewhere around here, the function is neither increasing nor decreasing. It is constant, and then it increases continuously. And we can also have and actually I'll do it down a little bit here so we can see it. We could also have an example of where our function is decreasing. So our function's decreasing continuously and then goes down here. So if we notice here, the function is increasing, it's increasing, so our slope here is positive. It's positive from here going up all the way to this critical point, and then it still keeps going up. So we know the function is still positive. The slope of the tangent lines are still positive. If we examine this, we know that f of x up until this point is increasing, and then it continues on increasing. Our derivative will be positive because our slope is positive, and then it continues on being positive. So here, even though we have what I call a horizontal tangent line at this point, because the function is not increasing nor decreasing, that's supposed to be horizontal. But we know that the derivative is not changing, so we do not have a max or min. And the same thing respectively goes for a point here. Our slope here is negative because our function is decreasing. Our slope here is also negative, our function is decreasing. So we recognize that we have no change in slope. So in this circumstance, as we go down, if we look at this, our functional value is decreasing, and then it continues on decreasing. So it's decreasing, 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 hits this critical point, and then keeps on decreasing and decreasing, which means that our derivative, f prime of x, which is the slope of the tangent line, will be negative, and then will continue on to be negative. So these will, in fact, give us zeros of our first derivative. These will in fact give us zeros. However, they are not any relative extrema. They are not any values that give us a max or a min. So now in order for us to do this example, we recognize that we are going to have to find the first derivative, and then set that derivative equal to 0, because when we set it equal to 0, we get all of these possible critical points, maxes, mins, and horizontal tangents, even though that's not what we're looking for. So let us go ahead, and I'm just going to copy this. I'm going to copy this so we can see it. Let's go ahead and copy this to our next page. There we go. So let's go ahead and work this through and see how we do. So first of all, we're going to find our derivative f prime of x. And just as a reminder, some of our derivative rules, we know that the derivative of x to some nth power, where n exists as a real number, but n does not equal to 0 because that would be trivial. X to the 0 power would be 1, and that would not apply in this circumstance. We know this would equal to n. We bring down the n as a value of the coefficient times 1, and then we're going to get x to the n minus 1 power. We subtract our exponent by a value of 1. And also we look at that 11286 at the very end over 15, and we recognize here that, that this is a constant. So we know the derivative of a constant is equal to 0. So let me just go back and review exactly what we're looking for in this problem. First of all, when we look at this problem, we're going to be finding the intervals which our function's increasing, the intervals on which our function's decreasing, so it's going to be increasing, and if this function would also be increasing here, if we were looking at this function, it's decreasing from here to here, and then we have to identify the relative extrema, any relative max or any relative min problems. So in order for us to do this, we have to find our derivative. So we're going to find the derivative of this function. So we're going to set this guy equal to, we're going to eventually set him equal to 0, but we're going to find the derivative first. So we're going to bring the exponent 65 down as a coefficient, multiply it times 1/65, we get a value of 1. So we're going to get x to the 64th. And then we are going to subtract off. We're going to subtract off. Let me just get rid of this cursor here. We're going to subtract off 4/63 times 63, which gives you a value of 4, x to the 62nd power, and then we know the derivative of this nasty looking constant just gives you a value of 0 because we're applying our derivative rules. So now this is our derivative. This is f prime of x. In order for us to find the maxes or mins, we know that f prime of x will equal to, I'm sorry, not f prime of 0, f prime of x equals to 0 will give us any relative maxes, any relative mins, and then also what I call horizontal tangents, and that's where our slope does not change. So f prime of x will not change. The function is constant, so f of x is constant. So it's neither a max nor a min. So in order for us to find this, we're going to take x to the 64th and subtract off 4x to the 62nd and set this equal to 0. In order for us to solve, we're going to pull out some of our algebraic skills and pull out an x to the 67th, and we're going to be left with x squared minus 4, still set equal to 0. Now since we factored out this polynomial, we can set them both equal to 0 independently. So we get x to the 62nd equal to 0 and x squared minus 4 equals to 0. We know x therefore will equal to 0 from this x to the 62nd, and we know x will equal to plus or minus 2, solving this polynomial x squared minus 4. So now we know that we have 3 critical points. We do have 3 critical points. However, we don't necessarily know if they are relative extrema. And in order to determine relative extrema, we're going to have to perform a sign analysis of our derivative. In order to determine whether or not these are in fact relative extrema. So in order for us to do this, we're going to determine and write our critical points in ascending order on a number line. So we're going to start off here with -2, 0, and then +2, -2, 0, and +2. And we are going to have corresponding factors of x to the 62nd, which I'm going to write up here. So my factors will be x to the 62nd, and then I'm going to have another factor of x squared minus 4. Some of you may have factored x squared minus 4 into x plus 2 and x minus 2, and that just means instead of x squared minus 4, you would have an x plus 2 and then an x minus 2. If you would have completed the problem that way, you would have still the same solution. It does not matter. So it is your discretion how you want to perform this sign analysis. I'm going to leave it as x squared minus 4 because at this level I do recognize solving that we're going to get 2 possible solutions of plus or minus 2. So now what we're going to do is that we're going to pick values. And I'm going to split this up, and I'm going to sort of partition this so we can see that there's going to be 1, 2, 3, 4 areas that we could have sign changes of our derivative. So now if we look at x to the 62nd, we recognize here that this corresponds to a value of 0. The nice thing about this guy is that since x is raised to an even exponent, we know that no matter where we are on the number line, we plug that in and x to the 62nd will always be positive. If we pick a value to the right of 0, that will be positive, and then to the right of 2 will be positive. Picking a value between -2 and 0, like -1, that will also be positive. Picking a value to the left of 2 will also be positive. So x to the 62nd, because he's positive, because he has an even exponent, will be positive everywhere throughout the number line. However, x squared minus 4 does not hold that same consistency. We recognize here that his critical values are negative 2 and 2. So we expect the x squared minus 4 factor to have a consistent value between negative 2 and 2 and have an opposite value on the opposite ends of negative 2 and 2. So picking a value between negative 2 and 2 and plugging it in, like 0, 0 squared minus 4 will be negative. Therefore, anywhere between negative 2 and positive 2, our x squared minus 4 factor will be negative. So picking a value like negative 1. Negative 1 squared is going to be 1. 1 minus 4 is negative 3. This will be negative as well. Picking a value like positive 1. 1 squared is 1 minus 4 is negative 3. This will also be negative. If I pick a value like 10, picking a value like 10 over here, 10 squared is 100 minus 4 will be a positive 96. Picking a value like negative 10 over here, we're going to have negative 10 squared, which will be 100 minus 4 is another positive value. So I have been able to determine my sign analysis just by plugging in values that fall between these domain values. So now if I want to determine my actual sign analysis, I'm going to multiply these signs together. So I know that I will have f prime of x by multiplying the positive times the positive, and that will give me a positive value. Here I will have a positive to the negative, therefore I will have a negative value. Here I will have a positive times a negative, this will also be negative. And then a positive times a positive will also be positive. So therefore, since I know my derivative, I know what my function's doing. Since my derivative is positive, I know my function must be increasing. Since my derivative is negative, I know my function must be decreasing. Since my derivative is negative, I know it must be decreasing. And then lastly over here, I know the function must be increasing because my derivative is positive. So at this point, I can actually answer parts A and B. I can actually answer parts A and B. It wants to know for part A where my function's increasing and part B where my function's decreasing. So if I look over here in part A, I know my function is increasing from negative infinity until negative 2. And then I'm gonna leave this blank because I want you to fill in whether or not we're going to conclude this value with a parenthesis or a bracket. Hopefully we recognize that at negative 2 our function is neither increasing nor decreasing, so we're going to leave this with a parenthesis. And then we're going to union or conjoin this from 2 all the way to positive infinity. And again, we can't include these values in our increasing or decreasing interval because at those 3 values our function is neither increasing or decreasing. We know that our function has a slope that's equal to 0. Therefore, we know he's not increasing or decreasing. For part B, it asks where the function is decreasing. We know he's decreasing between negative 2 and 0, not inclusive. And then again from 0 to positive 2, it's supposed to be negative 2, sorry. 0 to positive 2, not inclusive. And then part C asks for relative extrema. So let's go ahead and analyze our sign analysis to determine relative extrema. So let's look over here. We know our function is increasing and then decreasing. So he is increasing and then decreasing. He's increasing and then decreasing. So look what happens. Look what we form here. We have a relative max. He's increasing then decreasing. Notice here the function is decreasing and then he's decreasing again. So we do not have any change in derivative. Therefore, there's no max nor min. There's no relative extrema here. This is actually what I call a horizontal tangent. This function is just constant. It just plateaued. And then here, the function will be decreasing and then it increases. Whoops. It's decreasing and then, well, for some reason the screen pumped down a little bit. It's decreasing and then increasing. So at this point, I'm going to have a relative min. I'm going to have a relative min. So I recognize that I have relative extrema, and I'm going to have a relative min at x equals to a value of 2, at x equals to a value of 2, and then I'm going to have a relative max at x equals to negative 2.